Good afternoon, everybody. Hope you guys are having a good start to your Wednesday. I hope that your week has gone well. We're kind of, for this class, we're kind of at the end of our week. Um, I am going to go ahead and get things started with our starter questions for the day. Um, and I wanted to mention that I will be posting these on our Canvas page. Right now, there's a link to it, but that link goes nowhere. Um, I'll publish the page that the questions are already on, and then you'll be able to see those for when you study after or when you prepare for your exams and stuff. But in the meantime, here are the kind of get things started questions. Um, I'll keep my mouth shut for a little bit while you guys work on these, and then I'm going to leave them open for about 5 minutes total. Now go ahead and take your time to answer those, but I'm going to go ahead and get started in the lecture. Um, we are con we are going to continue talking about amino acids. The slide deck that we had yesterday, Monday, I'm sorry, had about 29 slides in it, and we got to about slide 15 or 16. I took the last half of that slide deck and copied it into the slide deck that I'm going to begin working with today. Now, I'm going to go full screen on this one. I've got those linked. I've got it as a PDF as well as a PowerPoint file. Um, this slide deck is simply titled Classification of Amino Acids and Titration Curves. Like I said, I'm going to leave these questions up for about 5 minutes, then I'll talk about them. Um, so, for our classification of amino acids, we've already talked about how to classify them. We talked about and referred to them by the terms like polar and nonpolar, polar uncharged, polar positively charged, and polar negatively charged. Those are the biggest ways in which you can kind of evaluate and classify amino acids. Now, if any of you are coming to this class from, say, like a nutritional background, you might be able to think about your amino acids in a slightly different way. And what I mean by that is you might, with a nutritional background, you might think about your proteinogenic amino acids. So these same molecules that we're talking about, the ones that are used to synthesize proteins, you might think about them as essential or non-essential because you're thinking about them from a dietary standpoint. Can my body produce these? In which case they are non-essential, or do I need to consume these as a part of my diet? In which case they are essential amino acids because you have to get them from an outside source. Now, those are just two ways in which, like, classifying them based on polarity is one way, classifying them by nutritional or dietary needs is another way that you can classify amino acids. Now, we will primarily talk about amino acids in this class, sorry, proteinogenic amino acids. Primarily in this class, we will talk about them based on polarity. And we'll talk about them as being polar positive, polar negative, polar uncharged, and nonpolar. Now, these first three amino acids that I want to go ahead and identify and isolate as your polar positive amino acids are lysine, histidine, and arginine. Now, what I think is an effective strategy for learning these structures is to say, yeah, I've got 20 proteinogenic amino acid structures that I need to know, but I'm going to break that down a little bit. I'm going to break it down into a group of three that I identify as my polar positive amino acids: lysine, histidine, arginine. From there, I'm going to go, well, what's the opposite of positive? Well, that would be my negative amino acids. My polar negative amino acids are aspartic acid and glutamic acid. Now, keeping this, or when we focus in on negative or positive? Remember, this is all based on, well, what is the charge at a pH of 7? Now, whenever I say that, what is the charge? Again, I'm stressing this portion of my amino acid. So just the so-called R group. Now, that's because our backbone is kind of irrelevant. It doesn't really matter when it comes to uh, protein-agenic amino acid classifications. Does the backbone of an amino acid ultimately play a role in how a protein folds or something like that? Absolutely. There is no doubt about that. But we're primarily interested in these R groups and how they interact with one another. Now, this gives us a way to basically look at 5 of those 20 proteinogenic amino acids. So we've conquered or basically looked at about a quarter of the molecules that we need to look at. Now I'm going to leave for about 1 more minute. The starter questions are up. I'm going to close them in about a minute, then I'll talk about them. Now, one of the things that is important to know about your proteinogenic amino acids and their polar positive residues is that there are several identifiers. One, we've got the full name, lysine. We also have a 3-letter code and a single letter code. Now, if you look at these, lysine, LYS, hey, that kind of makes sense. That seems like that would be compatible. The first 3 letters, how about that? That's pretty clever. K, well, K is close to L in the alphabet, so there's that information that might be worthwhile. But K as a single letter code for lysine, unless there's a silent, maybe not silent, but invisible K when you spell lysine, where'd that come from? Completely valid question. Now, we'll come back to that in a second. Histidine, HIS. Single letter code identifier for that is H. Arginine, ARG. Okay, and single letter code of R. Okay, so some of these are useful from like a mnemonic standpoint. Like I remember one good way to remember arginine is, oh, does it matter which R group? I'm sorry, I didn't see that whenever you initially asked it. I'm not sure about the context of that, what I was saying or what you're referencing, Natalia. Would you, if you wouldn't mind, kind of providing a little bit more text, I'd appreciate that. Do we need to know the letters for the amino acids as well? Yes. I want you to know the structures, the full names, 3-letter codes, 1-letter codes, and being able to kind of jump back and forth between those. Great question, Luke. So when we look at these structures, we've got these R groups, we've got the single letter code, the 3-letter code, the backbone. Just to give you an idea of, well, where I think it's a good place to be is I think that it would be worthwhile to be able to just kind of come up with the backbone kind of off the cuff right now. If you're not there yet, just keep that in mind. Okay, well, the backbones are all the same, so I need to be able to do that. Okay, so like when it's negative or positive, you mentioned look at the R group. Which one do we focus on? Great question, Natalia. What I'm getting at there, and I'm going to go ahead and end the poll, and I'll come back to those questions in a moment. This definition of pH of 7 and classification as a negative amino acid. What I'm saying is that aspartic acid and glutamic acid are your polar negative amino acids. And what that means is that at a pH of 7, these groups, this one and this one, those will both carry a negative charge. Now, if we go back 1 point, at one more slide, lysine, these are our polar positive residues. These R groups at a pH of 7 will also, they will carry a charge, but their charge will be positive. So right now I've got them all drawn. And the way that I draw my amino acids to just kind of give myself a baseline is I draw them at a pH of 1, and then I kind of pick off groups almost like I'm titrating protons away. I hope that answers your question, Natalia. If it does not, we're going to be working on this quite a bit today. Okay, Anna says, at what point should we get the structures codes memorized? Is this like test 1 material? Yes, it is. It is test 1 material. It's also going to be throughout the semester. Um, so the sooner the better. And this is almost like I always kind of think about your first biochemistry class and your metabolism class, which arguably is a second biochemistry class. I always kind of think about them as like your first year of French class or Spanish or whatever foreign language you elect to take. The second year and beyond, well, you're using what you did in the first year. So this is kind of the language and the verb conjugation of sorts. Um, so I hope that helpful. Okay, so the backbone is standard. It's going to look the exact same, but those R groups are a little bit different. For polar positive, you said the R group is positive at a pH of 7. Yes, I did. And I will stand by that. Okay. Now, the next amino acids that I'd like to talk about are aspartic acid and glutamic acid. ASP for aspartic acid, GLU for glutamic acid, and then the single letter codes D and E respectively. Okay, I like to bring these two up in part because whenever I finally decided, hey, Joel, it's probably important that you know your amino acid structures really well. Um, I took a more methodical approach to learning the structures. And oh, I'm sorry. Let me go ahead and I hope that's enabled the captions. Um, the more precise and methodical way that I learned them was I said, okay, what's the simplest amino acid that has some changes to it? And what I mean by that is what is the simplest amino acid that undergoes changes based on the pH? And I kind of decided that aspartic acid was the amino acid that I'd start with. Now, I started with that because we have an R group that is simply CH2 and a carboxyl group. Okay. I feel comfortable being able to draw a carboxyl group versus whenever it's protonated, when it's deprotonated. I know that a carboxyl group, when it's protonated, so in a low pH environment, it is going to have a charge of, well, 0. It is going to be neutral. And that was helpful for me also to say, all right, it's neutral and it's protonated. So protonated does not always mean positively charged. Now, that was kind of my baseline of, okay, ASP and single letter code D. Now, GLU and single letter code E. I learned aspartic acid and then moved on to glutamic acid because the structures are very similar. They both have a carboxyl group, but then glutamic acid has two CH2s, whereas aspartic acid has one. In addition to that, in addition to their structures being kind of similar, kind of foundationally, there's like a progression, not like a progression, there is a progression that the single letter codes have that I'm pretty familiar with. And I'm not trying to flex on y'all or anything, but I've known the alphabet for the better part of 37 years, maybe 38. So that's something I'm pretty comfortable with. And at this point in time, I've got three kids who are pretty good at their alphabet, and in large part, it's my wife, but I was also there to help them learn the alphabet. So that's also something that I'm gonna, be like, I feel good about which letter follows which letter. So that was kind of like a, hey, this isn't a structural relationship, but if I remember aspartic acid, glutamic acid, the letters are very close to one another. Their structures might be similar to one another. And that was kind of my thought process. Well, as it turns out, this woman right here, her name was Margaret Oakley Dayhoff. She was a bioinformaticist and a physical biochemist back in the 1950s. Now, that to me is like, oh, bioinfra, wait a minute. She was like a computational structural biologist in the 1950s. There are times whenever I'm like, yeah, NASA, it's crazy. They sent a rocket to the moon with the strength of a calculator that, is I can't even simplify it so much, but it's like, wait a minute. People who are doing were using computers in the 1950s just blow my mind because I know that those computers were like as large as a house. I mean, that's what I remember from elementary school and taking like a keyboarding class where it was like, hey, look at these Apple IICs that you get to use. 40 years ago, that computer or a computer was 17 times as large and 1/100th as powerful. And so it's like, oh, crazy. At any rate, my point is that Margaret Oakley Dayhoff was a computational biologist, a computational biochemist in the 1950s. And one of the things that she did was she studied protein dynamics. So, protein, basically how a protein moves and the energy associated with energy of protein movement. And when you think about, and I hope that at least, I hope some of y'all are familiar with this. And if you are, if you're like, yeah, that rings a bell, hit a 3 in the chat in just a moment. But when you think about computers in computing in the 1950s and 60s, remember you had these like, well, I haven't said my example yet, Daisy. I haven't said my example, guys. You shouldn't be able to relate to me at this point. Okay, are we tested on the people you have listed thus far? Yeah, I will ask questions about kind of people because they're relevant. There's like it's important. I think that it's just a little aside here, but I think that it's valuable for you to know them because it's almost like if you decided like if I said, "Hey man, I'm a really big basketball fan," and you said, "Oh, cool. Who's your favorite player?" And I said, "Oh, my favorite basketball player is without a doubt Troy Aikman." Anyone who's having that conversation with me is immediately going to go like, "Hmm, this person knows about sports, but I don't think Troy Aikman played basketball." And I'd be, "Oh yeah, whenever he would throw the 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 ball to the guy with the puck, oh man, he was so good at basketball." I would lose a lot of credibility. And so I want you guys to be familiar with some of these personalities and people that we talk about because of their impact, but also so that you're comfortable as a biochemist. Now, anyway, where I was going with computing in the 1950s and 60s was you'd have these cards and you'd put like these, you punch little codes into them and then you'd run it through a machine and you'd spend 5 hours making this card and then I would say 5 + 5 is 10. And you'd be like, oh, it was totally worth it. If you can relate or if you have any context for that, give me a 3 in the chat. If you're like, what are you talking about? I'll go with a Z. Okay, I got a Z. I got a couple Z's. Oh, flood of Z's. Well, I'm going to next class period. I'm making a note for myself. Um, Programming with cards. Okay. Oh, dang, you hit me with 5 Z's, or maybe that's falling asleep actively. Okay, so the point is that Margaret Oakley Dayhoff, whenever she was doing these long and elaborate calculations, she would basically have to type in the sequence of a protein, but she would have to use the entire name. And she was like, this is, I'm not lazy. Maybe I didn't let you know that I'm a biophysical chemist in the 1950s, so I'm clearly not lazy, but this is kind of cumbersome to type in the full name or to write in the full name to program something. And so she was like, there's got to be a better way. And because of her work, that led to adopting 3-letter codes and 1-letter codes, respectively. And I wanted to grab these papers because or get the titles of these papers because these basically include the rules, the like guidelines for how do we come up with a single letter code or what constitutes a valid or a good 3-letter code. Lou, we're not old, nor am I. And Life comes at you fast. That's all I'm going to say. Okay. So she was like, there's got to be a better way. And so then they kind of evolved to like adopting a set of rules and adopting, well, this is a good reason to have this as a single letter code. Now, I want you to know the single letter codes. I want you to know the three-letter codes. And we're going to go through them individually first for the polar amino acids, and then for the non-polar proteinogenic amino acids. Now, in general, the kind of priority was to say, well, what's the first letter of an amino acid? Or what's the first letter of the amino acid's name? Well, for serine, that got the single letter code of S. Threonine got T. Tyrosine, rats. We can't use T for that because threonine has already taken it. So then it was, okay, is there another letter that kind of stands out within that name that we can use? And for tyrosine, we went with Y. Now, cysteine got C, aspartic acid got D, and glutamic acid got E. I went ahead and jumped over to aspartic acid got D because, well, we've got aspartic acid, we've got asparagine, we've got arginine. Obviously, A is not going to work for all of them. In fact, on this page, A is not going to work for any of them. Aspartic acid got D, arginine got R, and for arginine and tyrosine, the idea was, well, is there a strong letter that could like is in the phonetic pronunciation of that name, is there a sound letter that really stands out? Arginine got R, aspartic acid got D, tyrosine got Y, histidine got H, lysine got K. Now, asparagine and glutamine. These, and I'm going to go ahead and say these two amino acids are polar uncharged. I want you to take a moment and go on a journey with me. Let's look at the R group for asparagine, and let's simultaneously look at the R group for aspartic acid. So the R group for asparagine starts with the CH2. The R group for aspartic acid also starts with a CH2. After that, there's a carbonyl carbon going to an oxygen, and lo and behold, aspartic acid has that carbonyl carbon going to a oxygen. Now, when aspartic acid has this OH to complete its carboxyl group, asparagine has, instead of an OH, it has this NH2. Now, that is a polar group, but it's not going to be protonated. So this would be a polar uncharged amino acid. Now, based on this journey that we just went on, can you see, give me a Y in the chat or a X in the chat if you disagree, a Y if you can see how asparagine and aspartic acid are similar in structure. Wonderful. So they've got features of them that are very similar to one another, and that's why they have names that are similar to one another. The single letter code for asparagine is N. And the way that I personally think about that is I think of aspartic acid. Okay, that's my acid, that's got my carboxyl group. Asparagine, okay, that's got my NH2. So I'm drawing basically the same thing, but I'm going to drop that OH and replace it with NH2. Now, the same thing goes if we look closely at glutamine and glutamic acid. Glutamine has two CH2s followed by a carbonyl carbon. Glutamic acid, two CH2s, carbonyl carbon, and the OH to complete the carboxyl group. Glutamine has that NH2 in place of that OH. So aspartic acid, glutamic acid are very similar to one another in structure. Asparagine and aspartic acid are very similar to one another in structure. Now, looking at these single letter code options, and especially thinking about, well, lysine was a K, asparagine is an N, tyrosine is a Y, glutamine. Hmm. What's the single letter code for that going to be? We haven't used the G, but spoiler alert, it's not G. The single letter code for glutamine, which I'm sure that some of y'all know, is close. We're not going to use any of the letters that we use for our nucleotides, or we're not going to use U. Glutamine is a Q. And if you're thinking, hmm, phonetic pronunciation might be a little bit of a stretch, but it's kind of helpful if you think about a good mnemonic for glutamine. And this is one I was told as a graduate student, but I was told glutamine is the cutest amino acid. And I was like, hmm, that's kind of a stretch. And then whoever I was talking with was like, okay, I just remember it as cutamine. And I was like, okay, that works. So glutamine gets the single letter code of Q. Now, for every amino acid here, we have SER, THR, TYR. Those are all unused, or those are all unique. CYS, unique. ASP, unique. Oh, but wait, it's not. So the three-letter code now. Three-letter code for asparagine and glutamine, we're going to have some conflict with aspartic acid and glutamic acid. So the ASP, the three letters for aspartic acid and glutamic acid, ASP and GLU, they get to go with those two amino acids. Now, I think, again, with respect to the structure in the three-letter code, there's some kind of simplicity and compatibility to it. Asparagine, the three-letter code is ASN. I always kind of think, oh, well, that's like aspartic acid, but with that NH2. So for asparagine, I think of aspartic. That's asparagus. That's nasty. Fair enough. Respect. Um, Glutamine. Well, glutamine kind of gets the same treatment. The three-letter code for glutamine is GLN. Natalia's question is, how were the single letter codes assigned? Well, the single letter codes, like I was saying on this previous slide, was we had these two papers that were published that gave the guidelines. And the first priority was, well, let's see if we can use the first letter of the name of that amino acid to be the single letter identifier without having redundancies. So aspartic acid, we can't label that as A because there's several other amino acids that start with the letter A. So then we went on to kind of what's the second idea? The second idea would be, well, is there a phonetic pronunciation that has a hard letter that you can use? And that's where this single letter code of D came from. And then, is there some structural similarity between an amino acid and another that makes another letter simple for it? And that's where the E for glutamic acid comes from, because thinking about the English alphabet, D to E, well, that's kind of a natural progression in terms of the sequence of the letters. And these two amino acids are very similar to one another. The only difference is this CH2 right here. So basically, to put it simply, the three-letter codes and one-letter codes, the rules for them are all here, but essentially that's what it is. And that kind of captures most of the amino acids. It's like, is the first letter used, or is there a phonetic pronunciation that uses a good letter alternative, something other than the first letter? Now, I want to go ahead and finish the three-letter codes. So we've done serine is SER, threonine is THR, tyrosine TYR, cysteine is CYS, glutamine is GLN, asparagine is ASN, lysine is LYS, histidine is HIS, arginine is ARG, aspartic acid is ASP, glutamic acid is GLU. Now, getting comfortable with these structures. I've kind of given, or I've intended to give you an idea of how to approach aspartic acid and glutamic acid. That gives you a way to understand the structure of asparagine and glutamine. Because if you know aspartic acid, then just aminate it, and you can make asparagine. Aminate it by adding that NH2 to it. Same thing goes with glutamic acid. Add NH2, and you've made glutamic acid into glutamine. Now, your other amino acids, there's there are some things that make them similar to one another. I want to go through this before I move on to the nonpolar residues. But I think that it's really great to find things that make them similar and then use that as your way of learning the structures. And again, what I'm scribbling out in red isn't really, or that's the backbone. That is the same for every single amino acid. So what you need to know is the part right here in this red circle. So serine, you might see it listed as CH2OH. The presence of that hydroxyl group is, well, what makes this amino acid polar. Threonine, well, that's CHOHCH3. We've got serine and threonine that both have an OH group on them. Those are our only two amino acids that have those alcohols. Tyrosine is a benzene ring plus an OH. So I misspoke immediately. It has an OH, but it's out from this benzene ring here. So tyrosine has basically a phenol ring, and that's what makes it kind of stand out. Cysteine is one of two amino acids with sulfur. Now, looking at that R group right there, I want you to think about that as, hey, that's pretty similar to serine. The only difference is we have a sulfur, which is yellow, instead of this oxygen, which is red. So that's kind of part of a strategy for learning the structures of serine, threonine, tyrosine, asparagine, glutamine, cysteine, aspartic acid, glutamic acid. If you're thinking about this from a standpoint of, well, I really want to know these and know them very well, what should I learn first? I would recommend aspartic acid, glutamic acid, then asparagine and glutamine, then lysine, histidine, and arginine. And then after that, I would group together threonine, serine, and cysteine, and then tyrosine at the end. So these are all kind of things that I would recommend doing. Now, before I lose track of this too much, I wanted to go back to the starter questions. I'm going to share the results on these questions. And these are just kind of questions of like, hey, where are you? I don't necessarily, I mean, by the looks of it, yeah, the most popular answer is the right answer in all of them. So question number one, you're looking at a protein that sits on the outside of a cell surrounded by water. So it's exposed to a polar aqueous environment. Which type of amino acid side chain would you expect to be most common on the protein surface? Well, you would expect polar residues to be in contact with a polar solution. So polar or charged is the correct answer. Two amino acids differ only in their side chain. One side chain has a formal charge at a physiological pH, so a formal charge, positive or negative. The other does not. Which property is most likely to be different between these two amino acids? So something that's polar versus something that does not interact with, or something that is charged versus something that does not have a charge. Yeah, the interaction with water. Last but not least, when amino acids are linked together to form a protein, they are often called residues. This is kind of changing the terminology that we use. This is like, hey, scribble out that backbone. What are we talking about? The correct answer for this is because only part of an amino acid remains after that bond formation. Because, yeah, the backbone is there, but that's the only part that really is significant for interactions with the environment. Okay, I'm going to stop the share there. I've got a couple of questions. I just want to make sure that I don't look at them. Okay. Um, Now I'd like to actually, I'll go ahead and launch this next question. And this one reads, which of the following is not a common classification for proteinogenic amino acids? We've already looked at a couple of them. Is it non-polar uncharged, polar positive, polar negative, or polar uncharged? Now, I'm going to go ahead and leave that up for another minute and a half, but I'm going to go ahead onto the next slide. Wait, can you explain three again for the beginner questions? Like what happens to the R groups? Well, the R groups remain in that solution. So they are interacting with the environment, they're interacting with other parts of the protein. So that's kind of the point of that one. Is that what you're looking for? Or if not, I'm glad to. Okay. Okay. So here are our non-polar amino acids. These are our non-polars, but also I've got these two that are examples of our aromatics. Now, one of the things that I want you to recognize about all of these amino acids is, and I say this both in jest and seriously. The part that I say in jest is these are boring. I mean, look at the side chains. They're not very exciting. And what I mean by that is kind of the serious part. Let's take leucine, for example. Leucine's side chain is just a bunch of hydrocarbons. What is that going to want to interact with in an environment, in an aqueous environment? It's going to want to interact with other hydrocarbons. So what that means is if we're thinking about a protein in three-dimensional space, this is going to want to be away from a solution. It's going to want to be away from the environment. So that part of the protein is going to kind of collapse inward. Now, to address the question about classification, the correct answer was non-polar uncharged. So if something is non-polar, it absolutely is uncharged. Um, but anything talking about charged or uncharged and non-polar, that's unnecessary. So we don't classify them as non-polar uncharged. Okay. And so now back to our non-polar amino acids. So we've got leucine, we've got all of these amino acids that mostly we're looking at hydrocarbons. Alanine, valine, proline is kind of interesting because the R group circles back to the N termini, but for the most part, all of these residues are going to interact with one another and they're going to want to avoid the environment. Now, in terms of the one letter codes, proline is P, valine is V, glycine gets the G, alanine gets the A, methionine gets the M, leucine, L, isoleucine is I, tryptophan, and phenylalanine. Well, these don't align. However, these are two examples that go back to that phonetic pronunciation. Tryptophan gets a W, and phenylalanine gets the F. Now, tryptophan, I remember always being like, I would always get tripped up on tryptophan versus tyrosine. And then in graduate school, someone was like, no, it makes a W. And I was like, it's kind of a stretch, but that works. So that was my good identifier for tryptophan. Now, the three-letter codes for these, proline is PRO, valine is VAL, glycine is GLY, alanine is ALA, methionine is MET, leucine is LEU, isoleucine is ILE. Don't fall for the trap and accidentally call that ISO. Tryptophan is TRP, and phenylalanine is PHE. Now, in terms of, well, what's a good strategy to approach learning these structures? Well, I think most people like to think about and like to take on glycine first because glycine stands out because it is the only amino acid that does not have an alpha carbon that is a chiral center. Notice how it's bound to two hydrogens. So this is not a chiral carbon. So lots of people like to learn glycine first, and then they look at alanine and say, oh, well, it's glycine, but with a methyl group. So we're kind of building something a little bit more complicated. Valine kind of makes a little V there with 3 carbons. Leucine and isoleucine, people like to group those together because let's see, 1, 2, 3, 4. 1, 2, 3, 4 carbons that make up those R groups. And well, isoleucine is simply an isomer of leucine. So then methionine is our why is it called isoleucine when it has a sec butyl group and leucine has an isobutyl group? I think that it's, Miles, I'm gonna have to get back to you on that. It's isoleucine, ILE versus iso. Miles, that's a great question. And I will get back to you on that one on Monday. So I apologize for not having a good answer off the cuff for that, but I will get back to you. So methionine is our other amino acid that has a sulfur in the side chain. The difference, or the biggest difference between methionine and cysteine is that, and people have a tendency to mix these two up, but remember that cysteine has this thiol group, this SH, whereas methionine has a methyl group on the other side of that sulfur. Tryptophan is our 2-ring structure, and phenylalanine is just the benzene ring. It's tyrosine without the OH. Okay, so there's our 1-letter and 3-letter codes for all of our proteinogenic amino acids. It's you guys are going to need to be able to identify these amino acids more so than be able to draw them. Um, there will be some opportunities, some instances where I'll ask you to draw something, and more than likely those are going to be a part of the discussions. But that's going to primarily be where that is. Okay, so now we're going to go back to our polar positive amino acids, lysine, histidine, arginine. We've got 3 ionizable groups. I previously mentioned that I'm not going to expect you to know pKa values, and I stand by that. What I do, however, want you to know, I'm not going to ask you to memorize them, but I do want you to have an idea, a rough idea of where they are. And what I mean by that is approximately what their value is. So the N-terminal pKa is typically around 9. So if I were to draw any random amino acid, I would expect the N-termini to have a pKa of about 9. The C-termini is going to be closer to about 2. Now, here are examples of values that I would provide for you on an exam. We'll have 3 ionizable group for lysine. We've got this 2.18 and then 8.95. And then our R group is going to be 10.53. Okay, so those numbers, roughly 9, roughly 2, and well, some kind of wild card almost, that's what I want you guys to know and be able to look at. I want you to also be able to identify, well, what are the possible structures of this molecule? So if we take lysine, for instance, lysine, one thing that I want you guys to be able to do is to be able to say, okay, lysine has 3 pKa values. So if I'm drawing a titration curve, I want 3 horizontal regions for it. 1, 2, 3. Now, scaling of these is something that I want you to be able to look at on actually on an exam. I'd want you to be able to critically look at a titration curve and tell me whether or not it is a valid titration curve. These numbers are the pKa values for all these different ionizable groups. So we've got 2.18, we've got 8.95, and then last but not least, we have 10.53. Now, one thing that I want you to recognize about this is I want you to be able to kind of critically look at two titration curves, knowing that lysine has three ionizable groups, three pKa values. I want you to look at it and say, okay, well, does roughly what are they? Which of these two, I'm going to go with A and B, which of these two titration curves is valid or, sorry, is a viable option? That's not drawn well, for lysine. Okay, so I haven't asked my question yet. So A or B? Now I'm ready for the responses. So which one of these, A or B? Can't see the curve. So both of these have three horizontal regions. But if you look at the scaling of this point versus this point, if we look and say, well, each of these is 2.18, 2.18, and this right here is 10.5, 10.5, well, then this one more than likely is about 8.95 compared to this one right here. So that's one thing that I want you to be able to do whenever you see, well, I'm not just looking for 3 points or, yeah, three regions on a titration curve. I want to know, are they approximately, or are they close in proximity to one another? Now, another thing that I want you guys to think about with respect to this is I want you to critically look at it and say, okay, well, which group gets deprotonated first as I'm titrating it from a pH of 1? Well, in this case, with lysine, the first group that's going to be deprotonated is my C termini. The second group is going to be my N termini. And then my third group is going to be my R group. So that's because 2.18, 8.95, 10.53, my pKa's increase in that sequence. So I'll deprotonate each one of those groups successively. If we move over to an amino acid like histidine, well, now I'm going to put these pKa values, 1.77. The N termini is approximately 9.18, and the R group is approximately 6.10. Well, when I'm deprotonating histidine, I'm going to deprotonate the C termini. Then I'm going to deprotonate the R group. Then I'm going to deprotonate the N termini. So I'm doing it in that sequence. I want you to think about that because that's going to have an impact on, well, at a given pH, is the side chain charged? Is it neutral? What is it? The way that we do this is, remember, what do I have all of your amino acids displayed at? What pH are they all shown at? Jack, you're right. 1. Every time I draw an amino acid, I'm showing it at a pH of 1. Every group that can be protonated is protonated. So these pictures, this right here, these are all at a pH of 1. And if you're looking at this and you're like, well, how am I supposed to possibly know that? Well, one way that you can know that is, let's think about a carboxylic acid. The pKa for a carboxylic acid is approximately, between 2 and 4, depending on what it's attached to. Is this carboxylic acid P protonated or D deprotonated? Add to the chat. The way I have it shown right there. It's protonated. Yes, it is. Okay. So if this is protonated, in this group has a pKa of approximately, let's just call it 3 for the sake of silliness. Not silliness, but let's call it 3. That group is protonated. That group has a pKa of approximately 3. This molecule, approximately what pH would it then have to be in? The solution that this molecule would have to be in, the pH would have to be below 3. Give me an R for right or a M for ma. I don't follow. So when we see something that's protonated, if we know the pKa, we can say, oh, well, it's protonated. So more than likely that molecule is drawn at a pH below that pKa. So every so just every time I show you a molecule as a part of lecture, I'm always going to draw it at a pH of 1. So they have to be an acidic. I'm just telling you how I draw them because that gives me a good baseline where everything is protonated. If you do it, actually, heck, I'll do this real quick. So if a molecule is deprotonated, the pH would have to be higher than the pKa, 100%. Let's see if I can find. Okay. Hmm. Well, no. Okay. So I'm going to switch my share because I want to compare and contrast the way that I'm showing you these molecules and the way that you might see it in other locations. And this isn't like, oh, I'm just going against the grain. I'm trying to be different for the sake of funness or to be different. I have no interest in that. But I do want you guys to be responsive to, hey, I know how Dr. Gray draws them, and I know how I see them in other locations. So if we look at these right here, can you please explain how you tell the pH just by looking at the structure of the amino acids? I absolutely will in just one moment. So if you look at these amino acids, and I'm just going to select, let's go with alanine. I just circled in blue this N termini. That group is protonated. This C termini is deprotonated. That's different than how I draw the molecules. And again, I'm not trying to be disruptive or challenging. I'm just trying to show you the way that I think is effective to learn the structures is by protonating everything. So now, if I told you that this molecule, this C termini has a pKa of about 2.1, and the N termini has a pKa of about 9.5. When the C termini is deprotonated, you'd be able to say, okay, well, the pH therefore has to be greater than 2.1. Give me a 1 in the chat if you agree with that and understand that. Now, if the pH is greater than 2.1, do I have an idea of what it has to be less than? And if the answer is yes, then add what that less than is, or what that number less than is. It has to be less than 9.5. Because the other group, the NH3, is protonated. And if that group is protonated, that we know that the environment is more acidic or is too acidic for that group to be deprotonated. So what I'm going to switch back to the slide deck. So all of the ways that I'm showing you these molecules, they are fully protonated. You can't put any more protons on them. And so if we take this arginine right here, I'm going to draw this arginine. Absolutely. If the pH is greater than the pKa, it's deprotonated. If pH is less than pKa, it's protonated. I thought it had to be below pH of 7, not 9.5. 7 is neutral, but we kind of don't care about 7 so much as we care about the specific pKa values. So if we look at arginine, we are going to look at the C termini of arginine. The C termini of arginine is 2.01. The way that I found that was I said, okay, arginine has the single letter code of R. R. Now, I know that the C termini is going to have a pKa of approximately 2. I've got this label here that says pKa of COOH, but also I just know that that C termini, and I want you guys to know that the C termini is going to have a pKa of approximately 2. So I'm going to put 2.01 here because that's what's in the table. The N termini, pKa of NH3, that's 9.04, which I know that that's going to be approximately 9, so that I'm fine with that. So this is 9.04. Now the last pKa value is 12.48, and that corresponds to my R group down here at the bottom, 12.48. So to answer the question, well, how do we know the pH based just by looking at the molecule? Well, we have to know, and you guys have to know about these different functional groups and being able to look at it and say, is it protonated or deprotonated? Our carboxyl group here is protonated. Therefore, the environment that this molecule is in has to be acidic. The pH, just as Michael added, must be pH is less than pKa. And if you're looking at this and you're thinking, well, I didn't see what the pH is, I'm not asking you to. Instead, what I'm asking you to do is say, okay, I'm going to use the context clues of, is that molecule protonated or deprotonated? Well, this is protonated. Therefore, my pH must be lower than my pKa. Does that make any sense? Okay. Okay. Would we be given a table like this on the test with the pKa's? 100%. I'm not asking you to memorize pKa values. Okay. So what I want to do, and the remainder of this slide deck is working through a couple of different things. It's 428 right now. I want to skim through this slide deck and show you what there is, but then I'm going to come back to this because drawing these amino acids at different pHs is a very important thing for you to be able to do. Here's our polar negative residues. Here's aspartic acid. This gives you basically just a place to practice drawing aspartic acid, glutamic acid. Then here are all of the pKa values. What I want you to recognize about this is that, well, most of your amino acids are diprotic amino acids. Do we have triprotic amino acids? Yes, we do. We've got, since the R group affects the pKa of C and N termini, is there any R group that drags the N termini below 7? If not, does that mean pH 7, the charge of the R group, is the overall charge of the amino acid because the C termini and the N termini That's a great assessment. That's a great question. Um, to answer your first question, are there any R groups that drag the N termini below 7? You can look at this and see that no, there isn't. Now, can you paint with a broad brush and say, well, what's the charge of this given the R group? That's a pretty reasonable approach, but one thing that you've got to be cautious of is histidine has this kind of unique classification. Histidine is classified as a polar positive residue, but, and this has to do with ratios, your R group with a pK of 6.1 at a pH of 7, is it all going to be deprotonated? No, in this case, we're dealing with most of it is going to be deprotonated. So most of it would be neutral, but for the purposes of kind of classification, it's still kind of grouped in as a polar positive because some of it will be positively charged. It's a fantastic question, Jack. Thank you very much for asking that. I hope that my answer helped. Um, okay. So, okay, great. So what I'm going to do is just go through, here's your proteinogenic amino acids that are polar, non-polar, and then this is just kind of a look at basically here's how you can play around with these things. What I want to do is I'm going to give you, or we are going to work through aspartic acid. Aspartic acid, ASP. This amino acid has pKa values, which I'll grab these numbers, 9.82, 2.10, 3.86. We are going to draw a titration curve for the triprotic amino acid, aspartic acid. We are also going to draw this molecule in all its different forms. So, aspartic acid, I'm going to draw the NCC that constitutes the backbone. NH3 and a positive charge. Remember, what pH am I drawing this molecule at? What do I like to draw all my amino acids at? pH of 1. Because then I can start out with everything is protonated. Then I'll begin deprotonating it because I'm going to read this from left to right. Okay, so NCC, here's my alpha carbon that I'm going to put a hydrogen on, then my C termini that I'm drawing my carboxyl group, and it's going to be protonated. Now, aspartic acid is CH2 followed by C double bonded O and OH. Okay, so there is aspartic acid. Now I'm going to switch colors so that I can write in my pKa values. The C termini has a pKa of 2.10. The R group has a pKa of 3.86. The N termini has a pKa of 9.82. Now, what I'm going to do is I'm envisioning that I have this in a solution with a very acidic pH of 1. And I am going to add potassium hydroxide or sodium hydroxide, and I'm going to make a nice titration curve. Start at 1. And what I'm going to do is I'm going to deprotonate these groups one at a time. The first group that I deprotonate is going to be my C termini because I'm going from a pH of 1 to higher. Could everyone give me a 9 in the chat if they follow that? Okay, great. Now the next thing that I'm going to do is I'm going to switch colors because I want to draw my molecule again, but now I want to show what happens after I deprotonated my first group. I'm going to draw NCC. My N-termini is going to get H3 plus. My alpha carbon's getting this hydrogen, and I'm going to give CH2, C double bonded O, OH. My C termini has been deprotonated, so I've got O minus. Okay, so after that, I'm going to write in my pKa values of the groups that remain, 9.82 and 3.86. I'm not going to write 2.1 because arguably I'm done with that. Now I'm going to draw another arrow, which is going to take me to my next molecule and my next form of my molecule. And the next group that I'm going to deprotonate with the addition of more of a strong base is going to be my R group. So my N termini has yet to change. My C termini has remained the same between my second model of it and the third. Got CH2, and now I've deprotonated my R group. Okay. Could you give me 5 in the chat if you follow this? Okay. Now I'm going to continue adding base, adding a strong base so that I can deprotonate the last group I need to deprotonate. The last group that I need to deprotonate is my N-termini. And whenever I deprotonate my N-termini, it goes from NH3 plus to NH2. C, C, O, O minus, then H, then CH2, and then C, O, O minus. Okay, so I forgot to write one of my pKa values. This is 9.82. I worked through this by eliminating a proton completely from one group, then moving on to eliminate a proton from the next group, and then finally eliminating a proton from the last group. Okay, now what I want you to think about, and I'm going to erase all my pKas now. What I'm curious about is, well, are there any other forms of this molecule, any other ionized forms of this molecule that exist at any other pH? Are there any other protons to remove? Give me a Y or N in the chat. It's really my question. Are there any other protons to remove? I'm getting Ys. Where? Oh, you got me. JK. Smooth. You're right. There aren't any others. I've taken care of all of the protons. Anna, you bring up the hydrogens on that nitrogen. I always kind of think about that the way I think about, well, remember in Gen Chem 1, you learned about ammonium. Ammonium versus ammonia. Nitrogen is super happy. It is content when it has 3 bonds to it. When it has 4 bonds to it, then it has a positive charge. Nitrogen's going to want to keep 3 bonds to it. If you remove one of these hydrogens, then nitrogen has 2 bonds to it. So you don't want to do that. Okay. So these are all the ways that we can depict this molecule. These are the bookends. Here to here. That's it. That's all that's been written. So if you look at this and say, okay, well, those are our extremes, one of the things that I want you to think about is on this far left end. Could anyone tell me what is the overall charge of that form of the molecule? On the far left side, right here, where I have a circle. Plus. Plus 1. The magnitude of that charge is important. Now, let's go to the far right. I'm going to draw another circle, and I need that circle to be filled with the charge, including the magnitude of that charge. Michael, you're absolutely right. -2. So then, let's see, we go from positive to 0. This is the form of the molecule that is neutral. And then this form of the molecule right here that I put a circle that I haven't added anything into, that's -1. So those are our possible charges of this molecule given from when we started, where it was completely protonated, to where it's completely deprotonated. Does anyone remember, or actually, before I get to that, I want to go ahead and draw the titration curve for this. We've got a total of 3 pKa values. Those pKa values were approximately 9.86. I'm writing those above these arrows. Or sorry, not 9.86. I need to start. I'm starting with the lowest pKa first, which is 2.10, 3.86, and 9.82. I'm going to draw 2 pK or 2 titration curves, and you tell me based on the color of it which is most accurate. We got a red one, and then we got a green one. Okay. Tell me R for red or G for green. Perfect. The first pK is approximately here, 2.10. The next one is about here, 3.86. And then the last one is here, 9.82. Those are my 3 pKa values. Now, what this shows us is, or what we can say is that we've looked at all the possible charges of our molecule, all the 4 variations of our molecule. Could aspartic acid have a +2 charge? Give me a Y or N to the chat. Nope. Could it have a -3 charge? Nope. Could it have a 0 charge? Yep, absolutely. Now, we talked about this number earlier, pi, or the isoelectric point. We can see what that molecule looks like. But the question is, well, a pi is a pH, where your molecule, where 100% of the molecule has an overall 0 charge. So what is our pi? Now, whenever you draw out your forms of the molecule like this, what you want to do is you want to find the pKa values that show your molecule transitioning from a +1 to a 0 and from a 0 to a -1 charge. Those 2 pKa values of 2.10 and 3.86, Sammy, I think you're just about right there. It's going to be halfway between them. Now, if you wanted to, and I'm going to erase this red titration curve, I'm going to write a letter, not like to my congressman or anything like that, but I mean, I'm going to write a letter, A, B, and C. Which one of those, A, B, or C, do you think corresponds to a pH equal to my pi? B. You're absolutely right. So if I were to erase this, I could say If I wanted to find my my PI, I'd say, boom, right there. That spot right there, halfway between these two pKa values. Now, what I want you guys to keep in mind is this is not a matter of, oh, well, I got to pick my lowest two pKa values, add those up, divide by two, and that is my PI. That's not how it works. You have to look at what are the possible charges of the molecule, and then what are the pKa values that flank the +1 to 0 and 0 to -1. Now, what I'm going to do right now is I'm going to open up the closer questions, and I'm going to leave those for you guys to answer, while I'm also going to go ahead and do yeah. I'm going to do something similar, but using a different amino acid. I'll give you about 30 seconds just to get some responses to those questions. I'll leave them up until the class is done. So if you're like, I'll read them later, that's fine as well. While I was giving you guys time to look at that, and I'm sorry this is unprofessional, but my wife sent me a picture of two of my kids next to each other, and I got to be honest, I don't know which one's which. Um, I think the one on the left was the newest one, but I can't remember. Um, so okay. Now what we did here, yes, copy paste totally. So what we did here was we drew out the molecules. And we went through kind of a deliberate process of looking at, okay, what is its possible charge at this pH? What about at this pH? What about at this pH? And what about this pH? I want to show you kind of a simpler way of approaching this. So I'm going to come back here and we're going to do this same thing. We're going to calculate the PI of the amino acid arginine. Now, if you remember, arginine is we called it the other day, PP or polar positive amino acid. Now, a kind of rough way to look at an amino acid is to say, here's our N termini, here's our C termini, so N, C, and then this is my R group. Okay. At an acidic pH, at a pH of 1, the N termini is going to have a charge of +1. So I'm going to put a plus there. At a pH of 1, my C termini is going to have a neutral charge. So I'm going to put a 0 with a slash through it on the C termini because that's my carboxyl end. Now, the last ionizable group is the R group for arginine. The R group for arginine, since it is classified as a polar positive residue, that is going to have a positive charge as well. So what that means is that I can say arginine at a pH of 1 will have a charge of +2. If you agree with that, put a 9 in the chat. If you're confused about that, put any letter. So what we're trying to do is we're trying to think about, without drawing the whole thing, what do these functional groups look like? The N termini looks like this, NH2 or NH3 plus. At a pH of 1, this is what the molecule, that's what the N termini looks like. The C termini looks like this. Or at a pH of 1, well, it's going to look like this right here. Now, just for the sake of, I'm going to show you arginine. This is what arginine's R group looks like at a pH of 1. So that's going to have a +1 charge. Now, if we jump ahead, if you're looking at this, okay, let's take stock of all our nitrogens just to kind of identify where that charge is. That nitrogen has 3 bonds to it. It's also got a lone pair of electrons. This nitrogen right here has 2 bonds to it and 2 hydrogens, hence the positive charge. So it's got 4 bonds going to it. This nitrogen has 3 bonds to it and a lone pair of electrons, but spoiler alert, this whole group down here, it's stabilized by something that starts with an R and ends with an resonance. You guessed it, resonance. So it's resonance stabilized. The point is that it has a positive charge there. I got a private message that says, how quickly are the recordings normally updated or uploaded? I try to get them in by 10 p.m. It's 4:51 p.m. If you got to go, I hope you have a wonderful weekend. I'm going to continue working through this and I'll record this and post this as soon as I can, but I don't need you don't need to stay. I'm sorry for not being done on time. Okay, so we've got the R group with a positive charge. This is at a pH of 1. Because remember, that's how I like to start them out. The N termini is positive, the R group is positive, the C termini is neutral. So what I'm going to do is I'm going to list out my possible charges. So one extreme is that my arginine, my amino acid that I'm kind of calculating the PI for, it can be +2. And when you deprotonate a group on that molecule, then it will have a +1 charge. After you've deprotonated that first group, you go on to deprotonate the second group, and that will give your molecule an overall 0 charge. And with 3 ionizable groups, well, we deprotonate our third group, and our molecule will have an overall -1 charge. So if you're looking at this and like, wait a minute, you drew 3 arrows and there's 3 pKa's. I feel like I'm noticing a trend. You absolutely are. What I always like to do is I like to take this kind of scheme and say, okay, well, it could be +1, it could, or +2, +1, 0, or -1. And then I like to take the pKa's and write those above the arrows. So 2.01. That's my lowest pKa. My next lowest pKa, could anyone add that to the chat? My next lowest pKa for arginine. After the 2.01 is 9.04. And then the last one is 12.48. Okay. Now, what I want to do is I want to find out, well, what's the pH where 100% of my molecule has a 0 charge? How could I do that? Well, do I care about all 3 of my pKa's for this purpose? Nope. Do I care about my 2 lowest pKa's? Nope. I care about the 2 that are surrounding my charge of 0. So I'll take the 9.04 plus 12.48, add those up and divide by 2. And whenever I do that, I get, 21 and a half divided by 2 would be like 10.65 or something like that. 10.76. I'm trusting your math there, Amy, and it sounds right. So this is like a quick way of doing almost the same calculation as this right here. I feel like an idiot. Okay, so the part I wasn't getting was how to get the number in between the two drawings. Lol. So we can always go with the numbers on the chart and use it to make each step. Yeah. And you deprotonate the smallest number up to the biggest. Yeah. That's why I like to start by drawing it at a pH of 1, because then I can say everything's protonated. Now I've got this sequential steps where my lowest pK, then the next lowest to the next lowest. That that is what I found to be very effective and helpful for not only myself but students in this class. Okay, I'm going to stop there and I'm going to say, I hope you guys have a great weekend. I will post this recording as soon as I can. And yeah, I'll see you on Monday. If anything comes up, please don't hesitate to email me, ask, and you know, I'll meet with you. Thank y'all.
Bye. Thank you.
Absolutely.